For the next 12-13 minutes, I want everybody to put on your thinking caps, your computation caps, your math caps, because this is where you are looking at a final exam question, or at least learning the most important part of neural network. Okay. So the main goal is I have chosen a differentiable loss, right? That means technically my whole loss is differentiable with respect to each parameter of my neural network. I may have lots of WIs for every layer, lots of BIs. I need to somehow update them, but WL depends on output of L minus 1, which depends on output of L minus 2. So the parameter at WL depends on the output of the parameters WL minus 1, and so on and so forth. All these parameters are intertwined and interdependent in complicated ways. How do I compute the gradients? And the algorithm that allows us to compute these gradients is called the back propagation algorithm, attributed to Jeff Hinton, came from the, I think, 80s or 90s. That time era has not changed till date. It's the exact same algorithm, okay? Because it's mathematically appropriate, logical, sound. Okay, so let me quickly go through the introduction, and then we'll do one example. Because of nonlinear activations, the combination is not convex. The learning problem is not convex. That's okay. Who cares? So we will basically do stochastic gradient descent with non-convex functions. What would it do? It will find a local minimum. Good. That's okay. To calculate gradients, we will use the chain rule. Okay. And the chain rule for calculus is derivative of loss with respect to A. If A computes B and B computes loss, would be derivative of loss with respect to B times derivative of B with respect to A. Okay, this is the general principle that we are going to use. And special name, backpropagation is nothing but a special name for gradient descent with chain rule in the context of a neural network and computed efficiently using dynamic programming. But we will not talk about the dynamic programming part today. But you can see, right? So for every node, so what we are going to do is we will convert the neural network into a computation graph, where at each point one weight or few weights is computing one particular new symbol, and I'll show you with an example. And so the base case would be derivative of the loss with respect to the loss is 1, of course. And we are going to use this notation A bar, which stands for derivative of the loss with respect to A. Okay. Now, for every node in the computation graph, so computation graph, think about forward computation. Okay. For every node in the computation graph, we wish to calculate the first derivative of loss with respect to that node. That node has only one symbol. For any node A, we want A bar to be del L over del A. After working forward through the computation graph, we will finally obtain the loss L. We will work backwards through the computation graph using the chain rule to calculate A bar for every node A, making use of the work already done for nodes that depend on A. As an example, if I have an edge from A to B, which basically means if I compute A, then I have some function that computes B, and I have already computed the loss with respect to B, which is B bar, then I am going to simply multiply this with the loss with respect of B with respect to A. So we will basically have B bar times del B by A, del B by del A. But multiple such B's may be computed from A. So A is a node which informs multiple nodes in the future, all the B's. So all those B's I will sum over. Okay. And the slide gives me one example, and let us look at this example. It says that suppose B is equal to A plus C. Then what is del B by del A? What is del B by del A? 1. C is not dependent on A, right? On the other hand, if B is equal to A times C, what is del B by del A? So therefore, in such situations, I will do b bar times 1 or b bar times c. Now, it also gives you an example of what if b is equal to tan h of a. So I thought we will just take 2 minutes and quickly do this computation just so that you know how to get these done. So what if b is equal to tan h of a, and the answer we are looking for is 1 minus b square. So I have quickly written down the equation for tan h of a. So tan h of a is nothing but 2 upon 1 plus e to the power minus 2a minus 1, and if you take the minus 1 on in the numerator, then it becomes equivalent to 1 minus e to the power minus 2a upon 1 plus e to the power minus 2a. So let us quickly compute del b by del a. So 2 over x, the derivative would be minus 2 by x square, right? So this will become minus 2 upon 1 plus e to the power minus 2a whole square, but now you have to take the derivative of x. So that is e to the power y, so that is e to the power minus 2a, but now you have to take derivative of y, which is minus 2a, so that becomes minus 2. So therefore, del b by del a is nothing but, and minus 1 of course when you take derivative has nothing. So you get 4 times e to the power minus 2a divided by 1 plus e to the power minus 2a whole square. Now you don't want to remember this. This is a complicated formula. So the book, the slide also says that this is nothing but 1 minus b square. So let us check. Okay, what is 1 minus b square? Let us use the if it is 1 minus b square, it should be same as 1 plus b into 1 minus b. And what is b here? B, let us use the second definition of b, it will make our life easier. So what is 1 plus b? 2 upon 1 plus e to the power minus 2a. And what is 1 minus b? Minus 2 e to the power minus 2a upon 1 plus e to the power minus 2a. No, there is no minus here, because I have already consumed the minus inside the denominator. And so if you do this, then this is nothing but 4 e to the power minus 2a divided by 1 plus e to the power minus 2a whole square. Right. So basically what have we done? We have taken the tan h function, and if you say, okay, suppose b was tan h of a, suppose b was a non-linearity here, and with respect to a, and then I want to back propagate the derivative of b to derivative of a, the derivative of a would be nothing but b bar times 1 minus b square. And of course in life we will be working with matrices and vectors. So all of these things would have an equivalent linear algebra notation, where everything is a vector and we are interested in a particular I at term of that vector, but then we will use it in the vector notation. Okay. Now I don't know if you have done calculus in linear algebra. Whether you have done it or whether you have not done it, you can verify it either which way. So here essentially what is going to happen is that if b vector is equal to a plus c vector, then it will still be the one vector. If b vector is equal to a dot c vector, now this dot, the special symbol is what is called the Hadamard product or the inner product, where the a vector and the b vector are multiplied element wise. They are also called element wise product. Okay. So then there it will become the b bar element wise product with c, and if it is 1 minus b square, then it will become 1 minus b Hadamard product with b, which is and then b bar will be also Hadamard product. Now this you can take from me on face value, but you can verify it in the slides. So now let us look at this particular example. Okay. Now in this particular example, let us look at what is it computing. Let's say xn is the input, and you compute wxn plus b and tan h on top of it. So tan h of wxn plus b is what E is. But we have split it into unit steps. So first xn came, w came, and that created wxn. Let's call it d. Now b came, and that we added b plus d, so that created wxn plus b. Let's call it a. Then we computed E equal to tan h of A, we call it E. Then let's say something else happened. Let's say we did a Hadamard product between V and E. So let's say f is equal to v Hadamard product with E. Then let's say G is nothing but sum over all elements of this vector f to compute summation h fh. And let's say that computed the loss function ln. And that loss function would also have the goal output and the intermediate output. Let's say this intermediate output is a number and we want to make this number as close to yn as possible. Then the loss function would be yn minus g whole square. Right. And now remember del n over del n is equal to 1. Del n by del n. Okay. And the form of G will be function specific, the loss function specific. For example, if the loss function is yn minus g whole square, then the derivative would be minus 2 times yn minus g. This would be g bar. So therefore, the g bar computation we can't do, that depends on the loss function. If it's cross entropy, it will be the derivative of the cross entropy function. If it's a squared loss, it will be the derivative of the squared loss function, and so on and so forth. But let us say we computed g bar. Now our goal is to back propagate it all the way. This is the example that we have to work on. And let us start one step at a time. Now, if I know g bar, which bar will I compute next? F bar. Why? Because g depends on f. And in particular, g depends such that it is a sum of all the fi's or fh's. Fi's, let's just say fi's. So, derivative of g with respect to fi would be, because it's just a summation, it will be 1. So therefore, f bar would be same as g bar. Please try to work with me on this. This is where all your concentration is and focus is needed. Let's look at the second one. So what is f bar? F bar is nothing but g bar times the dot with 1, which is same as g bar. Okay. Now, f is computed based on v and e. F is computed based on v and e. So now we will next compute the v bar function. Now here we will use what we just studied, that if b is equal to a Hadamard product with c, then derivative of b with respect to a is c, right? And we have to do b bar Hadamard product with c for the actual back propagation. So therefore, v bar will be equal to right. So let's see if we can get somebody to answer this question. So what is v bar? G bar Hadamard product with E. Very good. Similarly for the other one, because they are symmetric. So V bar became G bar product with E, and E bar became G bar product with V. These are vector products. Now this is equal to E bar. Now that allows us to compute A bar, and because it's a tan h function, we can use what we just studied and do 1 minus b square or b dot b as our formula. So therefore, we are able to compute A bar as nothing but G bar dot V Hadamard product with 1 minus E Hadamard product with E. Now I have computed A bar. A is equal to B plus D. So derivative of A with respect to B will be 1, and derivative of A with respect to D would be 1. So therefore, the D bar will be A bar, B bar will also be A bar. Now we have computed. Now if you think about it, what is going on, What were the parameters that we had? W, B, V, these were my free parameters. And I have computed derivative of loss with respect to V, I have computed derivative of loss with respect to B, and I am now left with derivative of loss with respect to W. Okay. Now, this D bar is a vector. This xn is also a vector. But this Wi is a matrix. And the matrix and the vector xn are getting computed to compute the vector D. Now, I have to differentiate D with respect to Wij and then do it in the matrix form. Suppose I have computed the derivative of D. So, derivative of loss with respect to D, that is D bar, and let's say that comes out to be A bar because A was equal to B plus D. So, derivative of D is same as derivative of A, right? I mean D bar is same as A bar, not derivative of D. So, now the last question. So, now I am given that D is equal to W times X. Now, W is a weight matrix, D is a vector that I sent out, X is also a vector that I get in, and I have computed D bar, and now with this D bar I need to compute W bar, right. So, what would be the expression? Okay, so what did you get? No, we don't want X bar, wait. What do we want? Do we want X bar or W bar? Come on guys, this is not very hard. X is the input to the whole problem. So, we can't take derivative with respect to the input. The input is what the input is. Now, what is very interesting is that sometimes you have the input created by another process. In that case, you can take derivative with respect to the input, but that's extremely advanced. For now, X is the input. What are the parameters? W. So, we need the derivative of loss with respect to W, which is W bar. So, we need to compute W bar. So, what is W bar? Yes, Jay. Okay, very good. So, he has finally figured out, the final expression for the derivative, and that expression is correct, but for everybody else, let's look at a specific example. So, if you are like me who gets confused with linear algebra, it is slower, but it's always a good idea to expand it out and check what's happening. Okay, it's always, it gives you the clarity. So, actually what is happening is, let's say I have a 3 cross 3 W matrix, let's say I have a 3 cross 1 vector of x's, and then when I multiply them, I will compute again a vector of d's, which is again 3 dimensional, right. So, what is going to happen is, this is going to be the expression W11x1 plus W12x2 plus W13x3 will be D1, and so on and so on and so on. Now, the main point to realize is that Wij only influences, you can see this, Wij only influences Di. Okay. So, that is an important aspect, right. So, when we take derivative with respect to Wij, only Di derivative is going to flow back, the Di bar is going to flow back. Okay. So, and moreover, the derivative of Di with respect to Wij would be, the derivative of Di with respect to Wij would be equal to Xj, right, because it's a simple addition and a product, and the product is with respect to Xj. And now, let's say the back propagation D bar is flowing back. So, let's say I am given D bar. So, what I need to compute? I need to compute derivative of loss with respect to the W. Now, this is going to be what? The dl, the partial derivative of L by W is going to be a vector, a matrix, a number. How many W's do I have? 3 cross 3. So, therefore, this output, because it can be with respect to any one of these, is also going to be a matrix, right. So, let us look at any one of them, because if you look at any one of them, life would be easy. So, let us look at W21 for example. And look at this expression, and let's say I am given d bar. And remember, we multiply these things. So, what would be derivative of loss with respect to W21? Which derivative will flow back? Which bar? Which d bar? D1 bar, D2 bar, D3 bar? D2 bar, because look, W21 is only influencing D2, right? So, only D2 bar will flow back, and it would be multiplied with x1, because that's the derivative that we have just computed, which is the local derivative. So, basically I will get an expression like this. Everybody with me? Right? You have to get practice with this if you want to do deep learning. Especially if you don't want to use black box deep learning and you want to come up with new architectures. So, at least for people. Now, these things are becoming easier and easier. Deep learning is getting democratized, faster than you believe. Now, you can just say, okay, run a CNN as a API call, and then the whole CNN computation will happen and you will get some answer. If you want to run it at that level of abstraction, that's a different story. But if you want to understand what's going on, allow yourself to debug, come up with new architectures. If you come up with new architecture, I can assure you it will not work in the first instance, because you would have made one or the other mistake. You would have to literally go inside, figure carefully what is happening. Is the program computing the correct derivatives? Are the derivatives flowing right? Are there other out of bound errors or this, that, and the other? So you will have to really understand the math in order to be able to debug these things. So try to get some practice with this. Now we want to convert this into a linear algebra notation. So now I have to come up with 3 cross 3 matrix. Look, I have to somehow take one aspect which is d bar, which is a 3 cross 1 matrix, another aspect which is x vector, which is also a 3 cross 1 matrix. How do I convert these two to result in this 3 cross 3 matrix? I multiply, but I multiply them how? I multiply them 3 cross 1 and 1 cross 3, right? So basically that means that I can think of it as a multiplication between the vector d bar and the transpose of the vector x. This is sometimes also called the outer product. Okay. And when I do this, that's the final term. So, so d bar x transpose is the derivative of loss with respect to w, and d bar was a bar. So therefore derivative with respect to w when I back propagate would be a bar x and transpose. Okay. All right. So that sort of wraps up our understanding of back propagation. Again, at a highest level, each computation that the neural network is doing can be divided into a computation graph where at one node only one computation got done, either addition or a nonlinearity or a multiplication or whatever, dot product, whatever it is, right? Only one computation at a time. So when I say nonlinearity of wx plus b, we convert it into 3 steps. W goes in, x goes in, one multiplication, b goes in, one addition, nonlinearity goes in, or right, one nonlinearity. So 3 steps. So similarly, each neural network can be converted into a slightly larger computation graph, and then we back propagate the gradients at each step, multiplying the gradient that is flowing back times the gradient of the edge and adding for all outgoing edges. So I get from all outgoing edges gradients and multiply with all the local gradients, and add them, and that gives me the gradient of my node, and then I send it back. Okay. This back propagation algorithm, as I think I already said, became the basis for training these deep networks. Before back propagation algorithm, it was not clear how can we train such large network, because if it's one layer network, life is easy. You know the input, you know the output, you can figure out the weights. But in 2-layer network also, we don't know the output of the intermediate layer. We don't know the input of the next layer. So things are very hard to train. And if it's a very large network, we don't know exactly what the hidden layers are supposed to do. What should be the output at every step? We had no idea whatsoever. So how do we train these things? Well, this kind of a chain rule over derivatives became the basis for doing that. But even then it didn't work, and it finally got to work in the late 2010s at a level where we wanted it to. And then there were many reasons for it. Some reasons were algorithmic, which we will not get into. If you are interested, check out something called dropout. Dropout was one of the main reasons why initially deep networks started to do very well. There were many other ways to regularize these networks, because these networks can have many local optima, and not all local optima are very good. Then there were, so regularization is a very important branch of machine learning, which we are not going to talk about. And then the hardware was not very strong to be able to do all these computations at a large scale, and then data sets were also limited. So all these factors played a role. The three-way street of large data sets, strong GPUs, and good algorithmic practices came together in training these deep neural networks that we have now.